All right. So, the second part of this morning session is nanostructures 2. So, here we are going to deal with coarser particles of our magnetoelectric composites. So, in this talk, I am going to focus on coarser particles of nickel ferrite and barium titanate. Okay. And I am going to talk about assembling the coarser structure by two different means. One is using chemical self-assembly, the other is using DNA assisted assembly. So, we did this work with collaboration with our chemistry colleagues, both chemical assembly and the DNA one. Okay. So, let us see. So, the coarser nanoparticles, they were assembled chemically by attaching two complementary coupling groups. So, you attach one group to the ferrite, the other group to the ferroelectric, then bring them together in the presence of a catalyst and they form coarser structure. In the second one, with the DNA assisted assembly, as you know, the DNA has a helical structure. We were able to get functionalized DNA linkers. The linker, if you unwind the DNA, you get two strands, right? So, Yale has a lab where they functionalize the complementary strands, and we are able to get that. Then the two strands were attached to the ferrite or the ferroelectric, then you bring them together, then the DNA will hybridize, then that is how that assembly works. So, fibers, we already talked about it, and so the chemical self-assembly we used particles of barium titanate and nickel ferrite, and they were assembled and characterized by a variety of imaging techniques, including transmission electron microscope, scanning electron microscope, and also various scanning probe microscopy, including AFM, MFM, and SMM. And they were also characterized with magnetic and ferroelectric measurement techniques, and we assembled these coarser particles into superstructures in a uniform or non-uniform magnetic field. And of course, you have to study the nature of the magnetoelectric coupling. For that, we use P versus E under H, magnetodielectric effect, that is change in the dielectric constant when you apply a static magnetic field, or also the ME voltage coefficient. We did some theory, and then the theory predicted strong magnetoelectric interactions for coarser particles. For example, we did some simulation for a core of 50 nanometer barium titanate and a shell of 10 nanometer nickel ferrite, and we came up with very strong interaction strength through the calculation of ME voltage coefficient. Once again, these numbers were obtained for the parameters that are good for bulk materials, not for nanomaterials. So, these numbers are highly misleading because we did not know these magnetostriction and piezoelectric coefficients for nanoparticles. So, that is the shortcoming in this model. But in any case, the theory predicted strong interactions, and that was the driving force behind doing these experiments. Okay, so what is the procedure for chemical self-assembly of the coarser particles? The first step is to synthesize barium titanate and nickel ferrite nanoparticles. We did that for nickel ferrite by co-precipitation, and for barium titanate we did not make them. we just purchased from vendors. There are many companies that would sell nanoparticles of barium titanate, the size that you want. You can mention the size 10 nanometer or 100 nanometer, but there is always a range of particle size in whatever you get. So, all they guarantee is a majority of the particles will be that particular size, and there will be particles on the high and low end of the spectrum, but most of them will be what you want really. And then the second step is to functionalize these particles with two complementary groups. The groups that we used, one is called alkyne group, the other is acid group. Then you bring them together in the presence of a copper catalyst, and there is what's called a click reaction that happens, and that's how the core-shell structure is formed. And somebody who invented this click reaction, they were awarded the Nobel Prize some time ago. Okay. So, it's a neat technique. The key is if you assemble a core-shell particle, you have to make sure that it's stable at room temperature, because everything in the universe, it has a finite energy, that's called thermal energy. Anything at room temperature will have K times the temperature. K is the Boltzmann constant. So, the bonding strength should be large enough to overcome any thermal agitation or dissociation due to thermal energy. So, you need to make sure that the core-shell particles can overcome the thermal energy and they stay intact as core-shell particles, not dissociate into fragments. So, I do not want to go into the detail how these attachments are done. It was done by my students and postdocs. I did not ask them how they did it, but it was a long procedure. It takes a couple of days, and the procedure is described here. I do not think it is really important, but all that you do is it involves a variety of solvents and exposure to UV radiation and so on, and then rinsing with methanol and all those things. But at the end of the day, you have two particles functionalized with alkyne group and acid group. The question is, how do you know the attachment was successful? How you know that you have decorated your nanoparticles with two complementary groups? That is done through infrared spectroscopy. And what is shown on the left and the right is that the IR spectra before and after attachment, and these peaks that you see here, that is evidence for that the attachment did happen. Okay. So, these groups have specific signature in the IR spectrum, and you have to make sure that they do show up, and they did show up. So, we concluded that the attachment was successful. Then you bring them together in the presence of a catalyst. So, by the way, the two groups, one group attaches itself to the barium in barium titanate, the other one to the iron in the nickel ferrite, and the attachment is quite strong. It can overcome the thermal energy at room temperature, and then when you bring them together in the presence of the copper catalyst, the click reaction takes place, and the bond is very strong, and it can withstand any kind of thermal energy, at least until room temperature and slightly above room temperature. And you see some of the TEM images showing the core-shell particles, and the top one is it is 100 nanometer core of nickel ferrite and 50 nanometer shell of barium titanate, and you can do simple calculation which we did, and in this case in 2 dimension you must have 8 barium titanate around the core of 100 nanometer nickel ferrite, and that is what you see at least close to it. And the second one, the middle one is, we also used 50 nanometer barium titanate and 10 nanometer nickel ferrite, and you see the STM image of that. And the third one is 100 nanometer barium titanate, 10 nanometer nickel ferrite, and a cluster of that. But you have to be careful, you can't keep decreasing the particle size, because below a certain size, nickel ferrite would become super paramagnetic, it no longer ferromagnetic, and you lose the very property that you need for magnetoelectric interactions. If it is too small, there is hardly any magnetostriction in nickel ferrite, then you may get core shell particles, but there is no magnetoelectric interaction. Okay. So, the optimum size would be at least 20 nanometer for nickel ferrite or above, and the threshold for barium titanate is probably 50 nanometer to maintain the ferroelectric nature. And these are some of the X-ray diffraction. We made sure that we did not end up with any impurities, and this one is a SEM picture showing a core of nickel ferrite and a shell of barium titanate. You clearly see distribution in the size of barium titanate. It is not uniform, it is not just 50 nanometer, there are small ones and a bigger barium titanate. And we also did chemical analysis, and we made sure that we do have nickel ferrite and barium titanate in it. And these are scanning microscopy images for the core shell particles, and it's the capacitance image at a series of frequencies 2.3, 7.3, 14 and 19. As you see here, you see a very clear image of the core and the shell at this frequency, because this is where the impedance match between the particle and the tip of the SMM, that's very good match between the two. And also you see a very nice core, and the shell is of course made of nickel ferrite of different size. It is not exactly 200 nanometer, there is a distribution in the size, but you do have a core and a shell for sure. And this is SMM image for a collection of particles at 16 gigahertz, and all of them show a well-defined core and a shell. This is magnetic force microscopy phase image for core shell particles. The center is the core, which is the dark region, and the shell is the brighter one. So, we are sure that we did form a core shell structure under these conditions by chemical self-assembly. The next one is DNA assisted assembly. So, people are asking, why did you use DNA? So, the answer is, look at yourself. DNA is the building block for anything that is living creature. It can be a tree or an animal or humans, and everything grows according to what it should be. We don't grow fingers all over the body, it's where it is. So, it has the driving force to organize itself in a proper way. So, we thought that if you can use DNA to assemble these core shell particles, maybe it's easy to form superstructures. So, we didn't form any superstructure other than using a magnetic field to assemble them into films. but people in the future, they may take this initial study and build on it to make superstructures of these composites, hopefully. Okay. So the attachment works like this. As I told you, we got the complementary strands of the DNA from Yale. They are functionalized with alkyne already. So all we needed to do was attach A side group to nickel ferrite and barium titanate, then bring the DNA and these, and then attach the alkyne functionalized DNA to A side functionalized barium titanate or nickel ferrite in the presence of a copper catalyst. Then you bring the two particles with complementary strands of DNA close together, they will hybridize and form core shell structure. If you heat it up to 80 degrees, they will dehybridize and separate. So by heating and cooling below and above 80 degrees, you can either make core shell particles or make them separate. That was the whole idea, and we did just that. Yeah, so these are the two complementary strands of DNA attached to barium titanate and nickel ferrite. Then they are brought together, and then you cool it down to 25 degrees, they will hybridize, or you heat it up to 80 degrees, they will become separate. And these are some of the images for the core shell particles assembled with DNA, and you see a single particle with a core and a shell all the way to the left. The center one shows a similar core shell particle, and this one is a string of core shell particles, and this one is a collection of these particles. And we used magnetic force microscopy and scanning microwave microscopy, and the core shell particles are shown in the MFM topography and phase image here. And this is scanning microwave microscopy, and it can see through the core shell structure, and you see a very well defined core, in this case nickel ferrite, because the nickel ferrite has a much lower dielectric constant compared to barium titanate. So this is a capacitance image. So the capacitance for the shell will be the shell is made of nickel ferrite, so the capacitance is much smaller compared to the core. So the core looks here as a bright spot, and the shell as a dark one. This is AFM topography, and this is the capacitance image at 14 gigahertz. Okay. So these are core shell particles. Then we applied a magnetic field, then bring these core shell particles together to form a superstructure. And that's what you see here. So we just put these core shell particles in alcohol in different concentration, and then apply a magnetic field. They orient itself along the field direction. And this one is the case under very low concentration of core shell particles, but you see a very nice alignment along this line where the field direction is. This is at a little bit higher concentration. The streaks of these lines, they indicate the field direction, and the core shell particles do align itself along this direction. So that would mean that the nickel ferrite that we used was indeed ferromagnetic. Otherwise, it won't line up the way it is seen in these images. These are at much higher concentration of particles, and this is in a non-uniform magnetic field. So, as you see here, there are regions where the particles are concentrated. These are regions of high field gradient. So, the force is maximum along this region, and they line up in this. And these are at different concentration, and initially they were heated up to 80 degrees, then they dehybridize, then apply a magnetic field, cool them down, and they hybridize and then line up along the field direction. And especially this one looks nice. And also we assembled this in a rotating magnetic field. The magnetic stirrer, it was just rotating. You spread these particles and you see nice rings of these coarser particles under a rotating magnetic field. All right, so now we characterized these coarser particles in terms of magnetic properties and ferroelectric properties, and you see traditional M versus H expected for a ferromagnet. So, the nickel ferrite is indeed ferromagnetic. That is what we used in these coarser particles. And once again, the polarization is in the scale of nanocoulomb. It is much smaller than the barium titanate film or bulk material. So, the piezoelectric effect is rather very weak in these nanoparticles of barium titanate. So, we measured the strength of the magnetoelectric interaction by two different means. One is low frequency magnetoelectric effect. You are familiar with this. These measurements were done on 2D films assembled between two copper electrodes that are shown here, or assembled between two copper plates. This is a 3D film. So, see, for the 2D film, the interaction strength is very weak. It is reflected in the value of the voltage coefficient, which is in microvolt per centimeter Ørsted. In the 3D film, it is millivolts per centimeter Ørsted. It is still small compared to bulk materials, but it is it's a factor of 100 or 1000 better than 2D film. And this one is also a 2D film, this is 3D. So, the maximum value that we got was around 16 millivolts per centimeter Ørsted. You should compare that with a bilayer of nickel ferrite PZT, which is in hundreds of millivolts per centimeter Ørsted. So, in the nano system, the interactions are much weaker than in bulk composites or thick film composites. So, the second method we used is what is called magnetodielectric effect. Here we used special instrument capable of measuring the dielectric constant at very high frequencies, at microwave frequencies. So, you make the measurement with and without a static magnetic field. So, when you apply a static magnetic field, it will change the polarization, that will in turn affect the value of the dielectric constant, and that is what is measured in this procedure. So, it is called magnetodielectric effect, and you see here, this is the dielectric constant measured as a function of frequency, and what is shown here is frequency range of 16 to 18 gigahertz, and that is the relative dielectric constant under 0 magnetic field and 2 and 4 kilohertz. You calculate the change in the dielectric constant and then plot the fractional change versus frequency, and this is the fractional change for a field of 4 kilohertz, and it is negative because the dielectric constant decreases when you apply a magnetic field. It's about 1 to 2%. And this one can also make the sample in such a way that it is in the form of a ring or a platelet. Then it has what is called dielectric resonance. This is dielectric resonance. Then under this resonance, the dielectric constant goes through a profile like this. Then you apply a magnetic field 2 or 4 kiloarstud. Then find the decrease in the dielectric constant. Then plot the fractional decrease in the dielectric constant. It will show a peak through the resonance frequency, and this value here is close to 25% versus 1 or 2% here. So the overall magnetodielectric effect is amplified under this resonance. Right. So we also made a disk of these Korshal particles and then measured the polarization versus electric field with and without a static magnetic field. So the change in the remnant polarization, the fractional change, is plotted here as a function of h. So there is hysteresis in it. There is an increase in the fractional change with increasing static field. Then it goes up to a maximum of around 7%. For decreasing field, the value keeps increasing until it reaches about 14%. This is for barium titanate, nickel ferrite, DNA assembled disk. We also sintered these disks at higher temperature. The sintering, we thought it will give better compaction and a larger magnetic field induced polarization. We were somewhat correct. Here the maximum value is 20%, 14%. So after sintering the disk, there is an enhancement up to 20%. That's all. So, the question is, how does the Korshal particle behave compared to a bulk composite? So, instead of Korshal particles, what we did was we took nickel ferrite, maybe 20 nanometer, let's say, and then barium titanate 100 nanometer, mix them together, make a disk. They are not assembled into Korshal structure. They were just mixed together and then sintered at high temperature, and the measurements were done on those disks. That's the H-induced polarization. The maximum value here is anywhere from 4 to 8% compared to 14 to 20% with Korshal structure. So the Korshal structure does influence the nature of the magnetoelectric effect, and it enhances the effect in the way the structure comes up. If it is Korshal structure, it shows a much stronger magnetoelectric effect compared to just a bulk composite with random distribution of these two phases. Right. So this is the summary of what it discussed right now. We are able to assemble and demonstrate that our effort to synthesize particles with core of one phase, a shell of the other phase, we did succeed, and we followed two different procedures. One is chemical self-assembly, the other is DNA-assisted assembly, and then these particles were imaged by different techniques just to make sure that we do have the Korshal structure, and we are able to form superstructures in the form of thin films, 2D as well as 3D, and we made measurements of the strength of the magnetoelectric interactions, and from the values that we got, we infer that there is indeed a strong magnetoelectric effect, but not with a strength anywhere close to bulk thick films or thin films of these composites. So that is the take-home message from this effort. And I'll answer any questions you may have.
What is the difference between magnetodielectric effect and magnetoelectric effect?
Magnetoelectric effect is, you look for the change in a voltage produced in the structure because of mechanical strain, right? So, whereas in the magnetodielectric effect, you look for a change in the dielectric constant. That's the only difference. But both are measures of the strength of magnetoelectric interaction. So, you are measuring different parameters to come to the same conclusion, essentially.
Both will give same conclusion. Both effect, like magnetodielectric measurements and magnetoelectric measurements will give same conclusion about that.
Yeah, you can draw the same conclusion, of course. Because depending on what facilities are available in the lab, they can follow either one. So, people do all sorts of measurements. And we did have the facilities, so we just measured.
You made some theoretical estimates before designing the structures and all. You made theoretical estimates.
Yeah, but it's not a
And the formula
proper.
can change at nano level, nano region and all. That because D33 coefficients and all were, those formulas were formulated for.
It will change because the geometry is different,
Yeah, that's
the mechanical connectivity is different. So depending on the structure, everything changes.
right.
There is no universal formula. So you have to come up with, that's.
Then how can this for a formula be valid? Like how it was cross-checked and verified? Like these estimates you made.
We published all those formula. It's available in the literature. Yeah, so each configuration has its own equation for all these effects. So the magnetodielectric effect I talked about.
Mechanical coefficients were taken into these coupling coefficients were taken into consideration when
Yeah.
this estimation and all.
Right. And also you use all the bulk values for Young's modulus, stiffness, all those things. But they are not exactly true because we don't have the numbers for nanomaterials. So that is a basic drawback in all these
It
calculations.
even requires tensor algebra and all.
Yeah, the formula is correct, but the numbers that you plug in, they are not correct.
Right.
So,
Even I tried once for my particular samples, but I was lost.
yeah, if somebody can come up with the Young's modulus, all these parameters, magnetostriction and piezoelectric coefficient for nanoparticles of ferroelectrics and ferromagnets, the formula is already there. You can plug into those formula and come up with a number and then make comparison with whatever you measure. But otherwise, those numbers right now.
But I think to the best of my knowledge, nobody has reached the ideal values or something.
No.
Experiments have their own limitations.
Yes, yeah, there are limitations, of course, yeah. But we mentioned that in the papers. We do say that these are using.
Recently published, the paper recently published.
It was all the references are there. Yeah, right. So it's 2016, 17. So all this nano stuff is from 2014 to 2024. Any other questions? All right, thank you very much.